two tones. From Institute of Power Chemistry, Chemistry and the Field of Science.
Thank you, Mr. Chairman. I'm very glad to be here to attend this symposium. My topic today is about active synthesis on iron, manganese, ultrafine techniques. I'd like to divide my talk into four parts. In the first part, I will give a brief introduction to the prism work. And the second part is concerned some general descriptions about the experiment, followed by the third part without some discussion, and the fourth part, conclusion. As we know, iron-based catalysts have been used in commercial facial chalk synthesis, and manganese has been regarded as one of the most effective promoters for enhancing selectivity to night oxides. The catalysts were conventionally prepared by co-precipitation or decarbolination. In our first work, a special degradation method has been used to obtain iron, magnesium, ultrafine catalysts. The impact of preparation parameters on active performance have been studied in this work, and the active phases and the role of magnesium have been demonstrated. Then let me recall some general descriptions about the experiment. This table breaks the catalysts used in this work. They are prepared by two different methods: the conventional decomposition method and the controlled degradation method, in order to add C and D respectively. And from different processors, oxidate, hydroxide, and acetate, and with different combination. This column is the surface area of the catalyst. The average part size measured by small angular scalar is listed in the last column. FT synthesis was carried out on a conventional floor microreactor. XRD was performed on a regard deluxe iron interactometer. Now, let's show you the results and discussion. I'd like to present the results. I'd like to present the results of the active synthesis first. This table just takes the effects of the degradation methods and the processor on the performance. Among the four catalysts from conventional decomposition, that's the lost activity. This indicates quite clearly that the controlled degradation is preferable for the preparation of catalysts with much higher activity. The net overall activity of catalysts from conventional decomposition is lower than that of controlled degradation. to say the control determination preferable for the operation of catalyst with better performance. On the other hand, among the catalysts from different precursors, the order of activity is H greater than O greater than A. This order is consistent with the BET specific surface area of the catalyst, implying that the active size increases with the specific surface area of the catalyst. The net overall activity of catalyst O is the greatest among the catalysts from different precursors, showing the effects of precursor on the selectivity. Now let me show you the effects of catalyst composition as illustrated in this table. As seen in this table, we can say that with increasing manganese content, carbon monoxide conversion decreases slightly again, and then decreases rapidly. Network method activity increases pronounced with the incorporation of manganese, and then remains virtually constant, but raises up when the catalyst contains low iron. Method selectivity decreases considerably and reach a minimum, but raises up again when the catalyst is manganese rich. The trend of carbon 5 plus hydrocarbon is reversed to that of metal selectivity. These results suggest that an appropriate amount of manganese can improve the network selectivity and decrease the potential of method without decreasing the activity considerably. Now let me go to the next part. The active phases and the role of manganese. In order to progress this program, we have to test the arc phases of the catalyst by using XRD at room temperature and pressure. It is shown from XRD that the catalyst is composed of high carbon and manganese oxide after synthesis treatment, which is independent of temperature and time of treatment. It is also indicated that the catalyst is composed of mixed spinolactase and manganese carbonate after reaction. That is to say, the active phases is continuous. The active phases are continuous changes during the continuous period. At the beginning, the active phase are high iron carbonate or manganese oxide, but they are stable and converted to mixed spinolactase and carbon and manganese carbonate by osmosis and migration with each other and reoxidized by carbon dioxide. and water. This program illustrates the active proposed as a function of reaction time during the condition period, indicating that the active performance is continuously altered as a result of continuous change of active phases. The role of magnesium. In our crosswalk, we have pointed out that magnesium has both electrical and geometry effects on iron-phase amplifier happiness. It has been mentioned about that magnesium is mainly presented as magnesium carbonate. In order to probe further the effect of magnesium carbonate, we have to have the active performance of a mixture of magnesium amplified atoms and magnesium carbonate with iron and magnesium atomic ratio of 3, as illustrated in this table. From compare the active performance of the mixture with the catalyst of OL3 magnesium 1P, which is listed in the second table. We can say that the mixture gives a lower activity and a much lower sensitivity to metal organs, but a much higher sensitivity to medicine. This indicates that only when magnesium carbonate is intimately contacted with iron containing phase can it improve the metal organ sensitivity and decrease the formation of medicine. It is very likely that only when intimate contact is that can appropriate coordination and interaction between iron and magnesium be overturned. In conclusion, I'd like to stress the following issues. First, iron, magnesium, ultrafine catalysts are active for active synthesis and with high level for natural organs, in which catalyst OL3 magnesium 1D shows the best performance. Second, active phases are continuously changing during the condition period, resulting in gradual alteration of active performance. 3. Magnesium is mainly presented as a magnesium carbonate in condition period, in reaction conditions. It can improve the metal organ sensitivity and decrease the formation of medicine by intimately contacting with iron containing phase. Thank you very much.
Again, I'd just like to caution you against comparing too much between catalysts and non-catalysts with conversions as high as 90% or even 95%. Because you have very severe thermal and mass transfer gradients in your catalyst bed. And I was wondering, Have you examined the top of the bed composition compared to the bottom of the bed composition? Because I would submit that the two are probably extremely different because of the difference in gas composition and temperature that exist in your canvas bed.
So I'm not very sure your question.
Well, I don't know if you didn't show any data for the top of the bed versus the bottom of the bed, but my caution here is that under such severe operating conditions, which are not used in industry anyway, you cannot run under conditions that high commercially in a normal reactor. Just to point out some possibilities at lower conversions, we have made iron manganese catalysts for every part. And one can very routinely use those catalysts and get olefin to paraffin ratios of 20 to 30 and even higher. So they're much more efficient catalysts than this for olefin production under more gentle operating conditions.
Are you asking about the effects of high-density composition? This one,
他问的是催化剂的反应器两头上跟尾巴这两头上造成有没有改变？因为转化率太高了，这个情况下面就是催化剂顶上的、催化底下的这两个头上有没有不同，有没有经过检查？
Jason Lee from Costa Korea. How much CO2 do you produce? And what is the molecular to chemical ratio in the high hydrocarbons? How much CO2 do you produce in your product? And secondly, what is the molecular to chemical ratio in the high hydrocarbons?
CO2. How much?
That's the